Hi, everybody. Glad to see you again. And let's start our lecture number 3, okay, on our astronomy course. The sky above seems to be a great blue dome in the daytime and a sparkling ceiling at night. Ancient astronomers believed the sky was a great sphere surrounding Earth, with the stars stuck on the inside like tumble packs in a sea. Modern astronomers know that the stars are scattered through the space at different distances. But it is still convenient to think of the sky as a great starry sphere enclosing Earth. The sky appears to rotate westward around the Earth each day. But that is a consequence of the eastward rotation of Earth. That rotation produces day and night. Notice how reference points on the celestial sphere, such as the zenith, nadir, horizon, celestial equator, and north and south celestial poles, define the 4 directions: north point, south point, east point, and west point. Astronomers measure angular distance across the sky as angles and express them as degrees, minutes, and seconds of arc. The same units are used to measure the angular diameter of an object. What you can see of the sky depends on where you are on Earth. If you live in Australia, you would see many constellations and asteroids invisible from Ukraine. But you would never see the Big Dipper, Большая Медведица. How many circumpolar constellations you see depends on where you are. Remember, your favorite star Alpha Centauri? It is in the southern sky and isn't visible for the most of the Ukraine. You could just glimpse it about the southern horizon if you were in Italy, but you could see it easier from Australia. This is a good time to eliminate a couple of common misconceptions. Lots of people, without thinking about it much, assume that the stars are not in the sky during the daytime. The stars are actually there day and night. They are just invisible during the day because the sky is lit up by sunlight. Also, many people inside that favorite star Polaris is the brightest star in the sky. You now know that Polaris is important because of its position, not because of its brightness. What you see in the sky depends on your latitude, as shown at right image. Imagine that you've been a journey in the ice and snow the Earth's North Pole, with the North Celestial Pole directly overhead. As you walk southward, the celestial pole moves toward the horizon, and you can see farther into the southern sky. The angular distance from the horizon to the north celestial pole always equals your latitude, the basis for celestial navigation. As you cross Earth's equator, the celestial equator would pass through the zenith, and the north celestial pole would sink below your northern horizon. Circumpolar constellations are those that never rise or set from mid-northern latitude, as is shown at left. You see a number of familiar constellations cycling polar and never dipping below the horizon. As the sky rotates, the pointer stars at the front of the Big Dipper always point toward Polaris. Circumpolar constellations near the South celestial pole never rise as seen from mid-northern latitude. From a high latitude such as Norway, you would have more circumpolar constellations, and from Kyoto, Ecuador, located on Earth's equator, you would have no circumpolar constellations at all. Astronomers use a simple formula to convert between magnitudes and intensity. If two stars have intensities 1A and 1B, then the ratio of their intensities is 1A over or divided by IB. Modern astronomers have defined the magnitude scale so that two stars that differ by 5 magnitudes have an intensity ratio exactly of 100. Very simple, right? Then, two stars that differ by 1 magnitude must have an intensity ratio that equals the fifth root of 100, which equals 2.512. That is, the light of one star must be 2.512 times more intense. Two stars that differ by 2 magnitudes will have an intensity ratio in the twice. It's about 6.3. And so on. Look at this one. Example A. Suppose star C is third magnitude and star D is ninth magnitude. What is the intensity ratio? Our solution will be next. The magnitude difference is 6 magnitudes, and the table shows the intensity ratio is 250. Right? Therefore, the light C star from star C is 250 times more intense than light from the star D. A table is convenient, but for more precision, you can express the relationship as a simple form. Look in this website. The intensity ratio I sub A over I sub B is equal to 2.512 raised to the power of the magnitude difference M sub B minus M sub A. Example B, if the magnitude difference is 6.32 magnitude, what is the intensity ratio? Let's make our solution. The intensity ratio must be 2.512 in power 6.32. A pocket calculator tells you that the answer is 337. When you know the intensity ratio and want to find the magnitude difference, it is convenient to solve the formula for the magnitude difference. Look at this one. Next example C. The light from Sirius is 24.2 times more intense than light from Polaris. What is the magnitude difference? Let's start our solution. The magnitude difference is 2.5 logarithm from 24.2. Your pocket calculator tells you the logarithm on 24.2 is 1.38. So the magnitude difference is 2.5 times 1.38, which is equal 3.4 magnitude. In addition to observe to the obvious daily motion of the sky, Earth's daily rotation conceals a very slow celestial motion that can be detected only over centuries. Over 2,000 years ago, Hipparchus compared a few of his star positions with those recorded near nearly 2 centuries earlier and realized that the celestial poles and equator were slowly moving across the sky. Later, astronomers understood that this motion is caused by the torque-like motion of Earth. If you have ever played with a gyroscope or torque, you have been seeing how the spinning mass resists any sudden change in the direction of its axis of rotation. The more mass is the torque and the more rapidly it spins, the more it resists your efforts to twist it out of position. But you probably recall that even the most rapidly spinning torque slowly sweeps its axis around in a conical motion. That is the axis of the torque pivot. So the axis sweeps out of the surface of a cone, and you can see from this. And this combines with its rapid rotation to make its axis sweep around in a conical motion called precision. It spins like a giant torque. Look at the right side. But it does not spin upright in its orbit. It's tipped on 23.5 degrees from vertical. Those large mass and rapid rotation keep its axis of rotation pointed toward a spot near the star Polaris. And the axis would not wander if Earth were a perfect sphere. However, because of its rotation, Earth has a slight bulge around its middle. The gravity of the sun and moon pull on this bulge, tending to twist Earth upright in its orbit. The combination of these forces and Earth's rotation causes Earth's axis to precess in a conical motion, taking about 26,000 years for one cycle. Because the location of the celestial poles and equator are defined by Earth's rotational axis, precision slowly moves these reference marks. You would notice no change or at all from night or year to year, but precise measurements can reveal the slow precession of the celestial poles and equator. Over centuries, precession has dramatic effect. Egyptian records show that 4,800 years ago, the North Celestial Pole was near the star Cuban, Alpha Draconis. The pole is now approaching Polaris and will be closest to it about 2,100 years. In about 12,000 years, the pole will have moved to within 5% of Vega Alpha Lyrae. Next time you glance at favorite star Vega, remind yourself that it will someday be a very impressive North Star. Figure C in this slide shows the path followed by the North Celestial Pole. You will discover in later classes that precession in common among rotating astronomical bodies. So, as a summary, astronomers divide the sky into 88 constellations. Also, the constellations originated in Greek and Middle Eastern mythology. The names are Latin. Even the modern constellations added to fill in the spaces between the ancient figures have Latin names. Name groups of stars that are not constellations are called asterisms. The names of stars usually come from ancient Arabic, though modern astronomers often refer to a star by its constellation, and a Greek letter is signed according to its brightness within the constellations. Astronomers refer to the brightness of stars using the magnitude scale. First magnitude stars are brighter than second magnitude stars, which are brighter than third magnitude stars, and so on. The magnitude you see when you look at a star in the sky, it is its apparent visual magnitude, which does not take into account its distance from the Earth. Flux is a measure of light energy related to intensity. The magnitude of a star can be related directly to the flux of light received on Earth and so to its intensity. The celestial sphere is a scientific model of the sky to which the stars appear to be attached. Because Earth rotates eastward, the celestial sphere appears to rotate westward on its axis. Are you agree with me? Now, the north and south celestial poles are the pivots on which the sky appears to rotate, and they define the four directions around the horizon: the north, south, east, and west pole. The point directly overhead is the zenith, and the point of the sky directly underfoot is the nadir. The celestial equator, an imaginary line around the sky above Earth's equator, divides the sky in half. Astronomers often refer to distance on the sky as if the stars, sun, moon, and planets were equivalent to spots painted on a plaster scene. These angular distances, measured in degrees, minutes of arcs, and seconds of arc, are unrelated to the true distance between the objects in light years. The angular distance across an object is its angular diameter. And now we will start today's new topic of lecture, cycles of the sun. In the previous lectures, you looked at the sky and saw how its motion is produced by the daily rotation of Earth. In this lecture, you will discover that the sun, moon, and planets move against the background of stars. Some of those motions have direct influences on your life and produce dramatic sights in the sky. As you explore, you will find answers to your essential question. What causes the seasons? How can astronomical cycles affect Earth's climate? Why does the moon go through phases? What causes lunar and solar eclipses? The cycles of the sky are elegant and dramatic, and you can understand them because you understand that Earth is a moving planet. That was not always so. How humanity first understood that Earth is a planet is the subject of a next lecture. Your alarm clock instrument that tracks the motion of the sun is the sky. Furthermore, your calendar is divided into months, and your calendar are astronomical that recognizes the monthly orbital motion of the moon. Your life is regulated by the cycles of the sky, and the most obvious cycle is that of the sun. The sun is rises and sets because Earth rotates on its axis, and that defines the day. In addition, Earth revolves around the sun in its orbit, and that defines the year. Notice an important distinction. Rotation is turning of the body on its axis, but revolution means the motion of a body around a point outside the body. Consequently, astronomers are careful to say Earth rotates once a day on its axis and revolves once a year around the sun. Even in the daytime, the sky is filled with stars, but the glare of sunlight fills Earth's atmosphere with scattered light, and you can see only the brilliant sun. If the sun were faint, you would be able to see it rise in the morning in front of the star. During the day, you would see the sun and the stars moving westward, and the sun would eventually set in front of the same star. If you watched carefully as the day passed, you would notice that the sun was creeping slowly eastward against the background of stars. It would move a distance roughly equal to its own diameter between sunrise and sunset. This motion is caused by the motion on Earth in its nearly circular orbit around the sun. For example, in January, you would see the sun in front of the constellation Sagittarius. As Earth moves along its circular orbit, the sun appears to move eastward among the stars. By March, you would see it in front of Aquarius. The apparent path of the sun against the background of stars is called the ecliptic. If the sky were a great green, the ecliptic would be the shadow cast by the orbit of Earth's orbit. That is why the ecliptic is often called the projection of Earth's orbit on the sky. That is why the ecliptic is often called the projection of Earth's orbit. Earth cycles the sun is 365.25 days. And consequently, the sun appears to circle the sky in the same period. And that means the sun traveling 360 degrees around the ecliptic namely in 365.25 days, travels about 1 degree eastward in 24 hours, about twice its angular diameter. You don't notice this apparent motion of the sun because you cannot see the stars in the daytime. But it does have an important consequence that you do notice the season. The season arises because of a simple fact. Earth's axis of rotation is tipped 23.5 degrees from the perpendicular to its orbit. As you study the cycle of the seasons, notice 2 important principles and 6 new tests. Because Earth's axis of rotation is inclined for 23.5 degrees, the sun moves into the northern sky in the spring and into the southern sky in the fall. That causes the cycle of the seasons. Notice how the vernal equinox, the summer solstice, the autumnal equinox, and the winter solstice marks the beginning of the season. Further, notice the very minor effects of Earth's slightly elliptical orbit, as marked by the 2 terms perihelion and aphelion. Earth goes through a cycle of seasons because of the changes in solar energy that Earth's northern and southern hemispheres receive at different times of the year. Because of circulation patterns in Earth's atmosphere, the northern and southern hemisphere are mostly isolated from Earth's other and exchange little heat. When one hemisphere receives more solar energy than the other, it grows rapidly warm. Now you can set your friends straight if they mention 2 of the most common misconceptions about the season. First, the seasons don't occur because Earth moves closer to or farther from the sun. Earth's orbit is nearby circle. Its distance from the sun varies by less than 4%, and that doesn't cause the season. Second, it is not easier to stand a raw air on end on the day of the vernal equinox. Have you heard that one? Radio and TV personalities love to talk about it, but it just isn't true. It is one of the silliest misconceptions in science. You can stand a raw egg and on and any day of the year if you have steady hand. I give you a hint. It helps to shake the eggs really hard to break the yolk inside so it can settle to the bottom. The planets of our solar system produce no visible light of their own. They are visible only by reflected sunlight. Mercury, Venus, Mars, Jupiter, and Saturn are all easily visible to the naked eye and look like stars. But Uranus is usually too faint to be seen, and Neptune is never bright enough. All the planets of the solar system move in nearly circular orbits around the sun. If you were looking down on the solar system from the north celestial pole, you would see the planets moving in the same counterclockwise direction around their orbit, with the planets farthest from the sun moving the slowest. When you look for the planets in the sky, you always find them near the ecliptic because their orbits lie in nearly the same plane as Earth's orbit. The planets whose orbits lie outside Earth's orbit move slowly eastward along the ecliptic as they orbit the sun. Mars moves completely around the ecliptic in slightly less than 2 years, but Saturn, being farther from the sun, takes nearly 30 years. Mercury and Venus also stay near the ecliptic, but they move differently from the other planets. They have orbits inside Earth's orbit, and that means they can never move far from the sun in the sky. As seen from the Earth, they move eastward away from the sun and then back toward the sun, crossing the near part of their orbit. Then they continue moving westward away from the sun and then move back, crossing the far part of their orbit before they move out east of the sun again. To find one of these planets, you need to look above the western horizon just after sunset or above the eastern horizon just before sunrise. Venus is easier to locate because it is brighter and because its larger orbit carries its higher above the horizon. What does Mercury? You can use the celestial sphere to help you to think about the seasons. The celestial equator is a projection of Earth's equator on the sky, and the ecliptic is a projection of Earth's orbit on the sky. Because Earth is a tip in its orbit, the ecliptic and equator are inclined to Earth other by 23.5 degrees, as shown in this figure. As the sun moves eastward around the sky, it spends half the year in the southern half of the sky and half of the year in the northern half. I hope you agree with that, right? That causes the seasons. The sun across the celestial equator going northward at the point called the vernal equinox. The sun is at its farthest north at the point called the summer solstice. It crosses the celestial equator going southward at the autumnal equinox and reaches its most southern point at the winter solstice. The reasons are defined by the dates when the sun crosses these 4 points, as shown in the table at the right. Equinox comes from the word for equal. The day of an equinox has equal amounts of daylight and darkness. Solstice come from the words meaning sun and stationary. Vernal comes from the word for green. The green equinox marks the beginning of spring. On the day of the summer solstice in late June, Earth's northern hemisphere is inclined toward the sun, and sunlight shines almost straight down at northern latitude. At southern latitude, sunlight strikes the ground at the angle and spreads out. Ukraine has warm weather, and United Arab Emirates has cool weather. Earth's axis of rotation points toward Polaris, and like a top, the spinning Earth holds its axis fixed as it orbits the Sun. And on the side of the Sun, Earth's northern hemisphere leans toward the Sun. On the other side of its orbit, it leans away. However, the direction of the axis of rotation does not change. Light striking the ground at a steep angle spreads out less than light striking the ground at shallow angle. Light from the summer solstice sun strikes northern latitudes from nearly overhead and is concentrated so vertically. Light from the winter solstice sun strikes northern latitude at a much shallower angle and spreads out. The same amount of energy is spread over a large area, so the ground receives less energy from the winter sun. The two causes of the seasons are shown at right for the someone in the northern hemisphere. First, the noon summer sun is higher in the sky, and the winter sun is lower, as shown by the longer winter shadow. And thus, winter sunlight is more spread out. Second, the summer sun rises in the northeast and sets in the northwest, spending more than 20 hours in the sky. The winter sun rises in the southeast and sets in the southwest, spending less than 12 hours in the sky. Both of these effects mean that northern latitudes receive more energy from the summer sun, and summer days are warmer than winter. On the other day of the winter solstice, in late December, Earth's northern hemisphere is inclined away from the sun, and sunlight strikes the ground at the angle and spreads out. At southern latitudes, sunlight shines almost straight down and does not spread out. Ukrainian Odessa and Crimea has cool weather, and United Arab Emirates has warm weather. Earth's orbit is only very straight elliptical. About January 3, Earth is at perihelion, its closest point to the Sun, when it is only 1.7% closer than it. About July 5, Earth is at aphelion, its most distant point from the Sun, when it's only 1.8% farther than average. And this small variation does not significantly affect the season. Next lecture will be the cycles of the moon. And for this moment, I hope you enjoyed our lecture, and I'm looking forward to see you next time. Bye.